All right, so today we're going to start section 4.1, Systems of Equations. And a system of linear equations is a set of two or more linear equations involving two or more variables. So usually we use x and y. A solution to a system is an ordered pair that will satisfy both equations in the system. So the solution of systems of equations is going to usually be an ordered pair. So if I give you a system of equations which has this fancy notation around the two equations, it's just showing you that is a system. And I give you these two equations here, and I'm asking you to check if the ordered pair is the solution or not. You're going to take the ordered pair. In this case, this is negative 4, 12. Oh, I'm writing 12. So negative 4, 12, which is x, y. And you would replace negative 4 in for x and 12 in for y for both of those equations to see if it works or not. So you would put it in for the first one, negative 2 times negative 4 plus 7 times 12, and see if that equals 46. And then 3 times negative 4 plus 12, and see if that equals 0. If it works for both equations, then the answer is yes. It is a solution to that inequality, to that system of equations. If it does not work, then the answer is no. So go ahead and take a minute, solve that out, see if it works or not. All right, did negative 412 work for the first? No, it didn't. So negative 2 times negative 4 is 8, and 7 times 12 is 84, and 8 plus 84 is 92. It doesn't equal 46, so it doesn't work here. It does work down here, but it has to work for both of them in order for it to be a solution. So letter A is not a solution. Let's try letter B. Doing the same exact thing, we're going to replace in now negative 2 in for x, and 6 for y, and see if this is equal to 46. And in the second one, 3 times negative 2 plus y, which is 6, equals 0. Well, negative 2 times negative 2 is 4. 7 times 6 is 42. And 4 plus 42 is 46, so it works for the first one. The second one, 3 times negative 2 is negative 6, and negative 6 plus 6 is 0. It works for the second one. So yes, this is a solution to that system of equations. In order to be a system of equations solution, it has to work for both. Basically, the solution to a system of equations is an ordered pair that satisfies both of the equations. There are 3 methods for solving a system of equations with two variables, and you've learned this in Algebra 1. You can graph the equations and see where they intersect. That is what we're going to be doing today. You can use something called substitution, which is using algebra to solve, and then using elimination. This is another way to use algebra to solve. Method 1, solving systems of equations graphically, is not the most effective because you obviously need graph paper. You need a straight edge. In a normal world, I would give everyone rulers so that everything was as accurate as possible. So it's not going to be the most effective or efficient, but it is the first method. So when we have equations, we're going to be graphing linear lines in this section. So we're going to have the same steps we had before, graphing the y-intercept, graphing the slope, but instead of having just one equation on a graph, we're going to have 2. And 3 things are going to happen, or can happen. The first thing that can happen is that we have 2 intersecting lines and they cross at one point. The solution of a system is the point in which 2 lines cross. So that's what you're usually looking for. Usually we'll get a single point of intersection, so just like our first example of figuring out which ordered pair was the solution, that second ordered pair was the solution because that's where those 2 lines cross. That's what's going to happen most of the time. The slopes of these lines are not ever going to be equal, which is why you have one positive and one negative in order for it to cross. There's going to be one exact solution for a situation like this, and we call this a consistent system. The second and third thing that can happen, and it's not going to happen as much, this is going to happen most of the time, but the second and third thing that can happen is that the two lines are identical. So that means that they might look different, because I wouldn't ever say, find the system or solution to y equals 2x plus 1 and y equals 2x plus 1, because that would be silly. Usually they'll look different. One will be in one form, one will be in another. And then if you go to graph it, you'll realize they're the same exact line. So they coincide, which means it's the same exact line. And that means that every single point on the line intersects with every other point because it's the same exact line, which we say that there's infinite solutions for something like this. This is called a dependent consistent system. The third thing that can happen is that these two lines are parallel, which means that they have the same slopes and different y-intercepts. There is no point of intersection for a system of equations with parallel lines because they never, ever, ever cross. And the whole point in doing this is finding that solution point where they do cross. So when you have something like this, that means there is no solution. This is called an inconsistent system. So the solution to the system corresponds to the point of intersection of the lines. A system of equations is consistent if it has at least one solution. A system is inconsistent if there are no solutions. And a system will have infinite solutions if the slope and y-intercept are identical. So that's a bunch of nonsense. But basically, I want you to just know there's either going to be one solution, infinite solutions, or no solutions. So to use the graphical method to solve systems of equations, you will need graph paper and you will need to graph these as accurately as possible so that you can find the actual solution. These have to be set up nicely so that the answer to the solution versus the answer to the system would be like 3, 1. It would not work out for these ones to have any decimals or fractions because you wouldn't be able to just estimate this. So I'm going to start the first one with you, and then I'm going to have you guys try B, C, and D. So for the first one, it's the easiest one, actually, because it's the only one that all of the equations are already set for y equals. The other 3, you will have to solve for y before you can do anything else. In letter A, the first equation, 2x minus 4, I'm going to start at negative 4 my y-axis. And then from here, I'm going to go up 2 over 1, up 2 over 1, up 2 over 1 to create this line here. Now, this is nice because now we're not in inequalities anymore. There's no need to shade a region. There's no need to worry about a dotted line or a solid line. This is just like a normal linear line. You would just then draw the line. But I suggest using a straight edge if you have something like a binder or a folder that you can use, because if not, your line is not going to be perfect, and the graphical method really requires you to be as accurate as possible. So I'm not even going to draw my line just yet because I know that it's not going to be perfect, so I'm going to come back to that. I'm going to change my color, and I'm going to do the next line. My next line starts at positive 1 on the y-intercept, for the y-intercept, and the slope is negative 1/2, which means I will go down 1 over 2, down 1 over 2. I can already see where this point of intersection is. After doing that, so I can you need a book? Is that the wrong one?
Oh, yes, I did.
Yeah, yeah.
It's supposed to Algebra 1.
Yeah, that's not it. Here you go. Alright, so after I have both of the lines graphed, I can see that the point that they intersect is right here. And that point is 2, 0. So it is really important that you double check your work to make sure that you didn't make a mistake somewhere. Like I didn't use a straight edge, so there's definitely areas where I could be making a mistake, and it's really important that you use the point that you get and test it to make sure that it's true by replacing an x and y in for both equations to see if it works. So let's replace 2 in for x and 0 in for y. So for the first one, this would be 0 equals 2 times 2 minus 4. Let's see if that's true. 2 times 2 is 4. 4 minus 4 is 0. That second one. Let's replace 0 in for y and 2 in for x. All right, we have negative 1/2 times 2 is going to be negative 1, and negative 1 plus 1 is 0, so this works here. So I know that I did not make a mistake. The solution to this system is 2, 0. So to solve systems of equations with graphing, you first have to graph both lines. To graph a line, the best way, and easiest I think, is to put it into slope-intercept form if it's not already. So for the second, third, and fourth one, you're going to have to solve for y first, and then you're going to have to graph them and then see where they intersect. Now with the next couple of problems, you are going to probably see situations where there's no solution or infinite solutions. If that happens and the lines are parallel, then there is no point of intersection, there's no solution. If you go to graph the line and you realize they're the same exact line, just written twice, then that's infinite solutions. So be on the lookout for that. So I'm going to have you guys try B, C, and D, and then we'll go over the answers together. All right, let's start to go over these. And then we'll move on to the next section part of it, which is substitution. So the first thing we have to do for each one of these questions is solve the current equation for y so that we can graph them. Now there are other ways to solve and graph from the way that they are currently in standard form, but I feel like the most common thing that I did each time was solve it for y, so I'll continue to do it that way. Negative 2y equals negative 2x minus 8, dividing everything by negative 2. My first equation in slope-intercept form is y equals negative 2 divided by negative 2 is a positive 1x, and then this is going to be plus 4. So graphing that first one, I'll go up to 4 on my y-axis, and then my slope is 1, so I'll go up 1 over 1. And just because I want mine to be as accurate as possible, and when I draw lines, it's not on here, I'm just going to make all of these points so that we can see exactly where the line will be crossing. Okay, there's my blue line. I'll come back and I'll draw an actual line through it in a minute. The next one is 2x plus 2y equals 4. Solving for y, I'll subtract both sides by 2x first. I get 2y equals negative 2x plus 4. Dividing everything by 2, I'm going to get y equals negative 2 divided by positive 2 is a negative 1x, and then plus 2. So in green, I'm going to start here at positive 2. And my slope is a negative 1, so I'm going to be going down 1 over 1, down 1 over 1, down 1 over 1. In the opposite way, I'll be going up 1 over 1, up 1 over 1, and so on. So when I graph this as accurately as possible, there's my green line, and then connecting my points to my blue line, I can see that these 2 points are going to be crossing right here. The point of intersection, which is the solution, is negative 1, 3. It looks like, but it's really helpful to verify that by taking negative 1, replacing it in for x, and 3 and replacing it in for y, and seeing if it works or not. You will know if you get these answers right every single time if you do that. So if I take the equations 2x minus 2y equals negative 8, I'm going to do 2 times negative 1 minus 2 times 3, see if that equals negative 8, make sure it works. And when I do that, 2 times negative 1 is negative 2, minus 6 is negative 8, so that one works. And then doing it for the second one, 2 times negative 1 plus 2 times 3, let's see if that equals 4. Well, 2 times negative 1 is negative 2, negative 2 plus 6 is 4, so yep, I didn't make a mistake, the answer is negative 1, 3. So it's always helpful to do that. I know it takes a little bit of time, but you'll verify and know for sure if you got it right or not by doing that. All right, moving on to the next one, letter C. The first step, again, is to take both of the equations and solve them for y. So for the first one, 3x minus 2y equals 6. I'll subtract 3x from both sides. I get negative 2y equals negative 3x plus 6. Dividing everything by negative 2. I get y equals positive 3 over 2x minus 3. So that part, I know I'm running through it, but I'm just solving for y. You guys should be great at that at this point. So I start at negative 3 on the y-axis, and from here I go up 3 to the right 2, up 3 to the right 2, because that's what my slope is. And going the opposite way, I can go down 3 to the left 2, and I'll come back and I'll connect that line in a second. My next one, 3x minus 2y equals 2. Solving this for y, I'm going to subtract both sides by 3x first. I get negative 2y equals negative 3x plus 2. Dividing everything by negative 2. I get y equals 3 over 2x, and then minus 1. So I can already see that these lines are very similar. They both have the same slope. I know lines with the same slope are parallel. This one starts at negative 1 though instead of negative 3, but the slopes are still up 3 to the right 2, up 3 to the right 2. So when I go to connect these points here, I'm going to quickly realize they're very close. You have to be really careful that you don't connect them over each other, but when I go to connect these lines, I can see that they're parallel. since they have the same exact slope, but different y-intercepts, which means these lines never cross, and the whole point in solving systems of equations is looking for the point that they do cross. So what would the solution be to this third one? Right, so this one's kind of funny because there is no solution, so the solution is no solution, since they are parallel lines. And you could actually tell at this point from when you solve for y that there would be no solution. So sometimes you might get out of having to do the whole graphing part unless I specifically ask you to. And then the last one, 2x minus 2y equals negative 8. Solving this for y, I'll subtract 2x from both sides of it. A lot of these look very similar. I get negative 2y equals negative 2x minus 8. Divide everything by negative 2. My first equation is going to be y equals 1x plus 4. So looking at my y-intercept, 1, 2, 3, 4 up with a slope of 1 will look like this. And I'll come back to connecting those points in a second. And then negative 2x plus 2y equals 8. Solving this for y, I would add 2x to both sides for this one. I get 2y equals 2x plus 8, and then dividing everything by 2, I get y equals x plus 4. So if I go to graph this one, I'm going to do the same thing, start at 4, slope of 1. I realize that these two lines are the same exact line. They just look different from the very beginning, but they actually are the same exact line. When you have this situation and you go to graph and you realize it's the same exact line, this answer is called infinite solutions. And that's because the lines are identically the same and they always cross because they're the same exact line. So that's how to solve systems with graphing. It is not the most efficient method because you obviously need graph paper, and not all of the time are you going to get integers as your answers. When you have situations where integers are not your answers, you're definitely going to want to use algebra instead. So one of the methods that you would use algebra to solve and not having to use graph paper and not having to rely on integers is a method called substitution. So we're going to be able to probably do one example together and then call it a day. But substitution its method is in its name. So you're going to be substituting something in to solve, and you're going to solve using algebra. So again, we're going to either have an ordered pair as an answer, or we're going to have no solution or infinite solutions as our answers. At this point, don't worry about labeling systems as consistent or inconsistent. I really just want to know what the solution is, if it's an ordered pair, or if there's no solution or infinite solutions. So, substitution. When you have a substitute teacher, that teacher comes into the classroom and replaces the other teacher for that day. Substitution takes an expression and substitutes it in for something else for that little time period. They're equal. Substitute teachers and your regular teachers are still equal. They both have a degree in something, which is why they're both able to be there in that room. They're equal, but they can replace each other. So when you're solving systems by substitution, the first thing you have to do is have one of the variables solved for. So I'm looking at the first example, and I have negative x plus y equals 3 and 3x plus y equals negative 1. The first thing that you want to do is pick one of the variables to solve for so that you can substitute it in for the other variable. Looking at these four variables, I have an x here, a y here, an x here, and a y here. You have four choices, but you want to make this the easiest choice, and you don't want to do too much work if you don't have to. Choosing one of these variables to solve for is very important because you want to make sure that you don't introduce any fractions or decimals unless you absolutely have to. Looking at these four choices, 3 of them would be fine to solve for, but one of them would be difficult because you would have to introduce fractions. And this 3x here, I wouldn't want to solve for that one because I know if I did, I'd eventually have to divide by 3 and I'm going to get fractions. However, if you solve for any of the other 3, that first x, that first y, or the second y, your answer will be nice and easy. It does not matter which one you solve for, but you have to choose one. So Sophie, which one do you want to solve for? The first one or the second one? this y, and the only reason is because Sophie wanted to do that one. But you could solve for the first x, the second y, or even the second x. It's just not, I wouldn't, because it's going to introduce fractions. So what we're going to do is choose an equation and choose a variable to solve for. We're choosing to solve for this y, and there's really no reason why for that. It's just, that's the one we chose to do. You have to choose one now. To solve for y, all I have to do is add x, and I'm left with y equals x plus 3. Y equals x plus 3 is the same exact equation as negative x plus y equals 3. It's just rewritten, solved for y. But now we have something that is equal. Y is equal to x plus 3. Y is the same thing as x plus 3. So if you think of it as like my example with the substitute teacher, your normal social studies teacher is equal to the substitute social studies teacher that comes in for the day. So you have two things that are equal. What you can do here is take what y is equal to, which is x plus 3, and replace it using substitution in for y in the other equation. So substitution takes something that's equal and replaces it in for something else. You cannot replace it in for the equation that you rewrote in the beginning, though. You have to replace it in for the second equation that you did not use. Y equals x plus 3. So for the second equation, 3x plus y equals negative 1. Since I know y is really equal to x plus 3, I'm replacing this y with what it's equal to, which is x plus 3. Once I do that, now you should see that you only have the same variable left. Once you only have the same type of variable, you can solve this equation as normal. 3x plus x is 4x. So I'm just going to solve this, subtracting 3 from both sides. I get 4x equals negative 4. Dividing by 4, I'm just solving for x here. I get negative 1 as my answer. That means that for this system, negative 1 is what x is equal to. So I know that the final solution to this equation is going to be negative 1, comma, whatever y is going to be. So I didn't have to graph anything. I just used substitution by taking one of the equations, solving for one of the variables, replacing that thing in for the variable, and then using algebra to solve. Now I know for sure that for this system, negative 1 is where these two lines cross. What you will now do is take negative 1 for x, because this is an ordered pair, and you're going to replace this negative 1 in for x in any of the equations. I would go back to the very beginning and choose one of the beginning equations because you know that these are the very original ones. But you can use the ones that you rewrote and that'll still work, but it really doesn't matter. This one's probably the easiest one to use, but it's up to you. Some teachers would say always go back to the original one. Some teachers will say use any one. It doesn't matter. Either way, if I use an original one, negative 1 in for x, if I use the very first one, negative x plus y equals 3. If I use negative 1 and replace that in for x, negative 1 will be here. And negative of negative 1 will really be a positive 1. So if I solve this equation, I would subtract 1 from both sides. I'm going to get y equals 2. If I use this equation, this is the easiest. Y equals negative 1 plus 3. You're going to get y equals 2. So I know that the y value of this solution is 2. The last thing you should do after you use substitution, then substitute your answer in to find the other one, is then verify that it works for both equations by replacing negative 1 in for x and 2 in for y into both of the originals. And once you verify that that works for both, then you know that it is true and you found the solution. So we will pick up where we left off tomorrow.